Okay, so in this video I'm going to do the proof of the training dynamics. So this is theorem 6. And there's two things we really want to do. So part 1 is show that. So we have this gradient descent rule, or this gradient flow rule rather, and we want to show that at the level of the function satisfies this differential equation, f of x theta t. So theta t are our parameters evolving under gradient flow, and x is any point, and if you do f of x theta t, that's some number, and it's evolving as the parameters evolve. And what we want to show is that it has this nice evolution in terms of the kernel. So this is the equation we want to show. It's what is it? It's alpha k of x y minus f of x theta t. So this is a 1 by nx row vector. This is an nx by 1 column vector. And when you add up overall the examples over the nx dimension, you get a number. That's the derivative of f. So this is how the model does on the training set. Training set. And this is the kernel K. Kernel K fed training set. And if you combine those, you get the evolution of f. And the point is that because f depends only on k in this funny way, we can actually exactly solve that. So part 1 is to show that it satisfies this evolution, and part 2 is to solve it. Part 2. So solve. And if you solve it, you just get the solution for all times. In theorem 6, we only wrote the final time solution. You can get any time, but the final time solution is nice. So after running this for however long you want, you get this answer in terms of the inverse. K of x times k of x inverse times y minus f of x theta t. Okay, so part 1 is going to be, why do we have this evolution in terms of k? Where does the k come from? What does it have to do with the evolution of f? And part 2 is, how do you solve it? So that's what we're going to do in this video. Okay, part 1. So the starting point is the loss function and the gradient flow rule. So the gradient flow rule, is this, the derivative of theta t is the gradient of the loss. And I'm going to be careful with my dimensions here. So this is an n par by 1 vector. And when you write down the formula for the loss, that is this, 1/2 the norm of f of x theta t minus y squared. This is that time t. N par by 1 vector. And now you have to know chain rule. So when you do the gradient of a scalar function, you can write that as a product of gradients. So normally people write the multi-dimensional chain rule as a big sum, but for us, I'm going to write everything in terms of matrices and vectors, so the sums are automatically handled by matrix multiplication. So I do think, I will say, I'll be honest with you, the way I get these is I usually write them out with sums and then go, aha, this is what it is, and write it out. So don't be embarrassed if you have to do chain rule by using sums. I think that's normal. But the final answer you can write nicely with multiplication. So here it is, minus alpha, the gradient of f times f. Okay, so this is an nx by 1 vector. This is an n par by nx matrix. And when you put them together, you get the n par by 1 thing. That's what we wanted. This was n par by 1. Okay, and this comes from the fact that the derivative of the squared function is just the original function. So the 2 sort of jumped down, canceled the half, and we got this vector f of x minus y that survived, and we had to multiply by the derivative of the inside, which is where this thing came from. So that's how chain rule worked. This is chain rule, but you should double check on your own, however you like to do chain rule, and make sure that it's right. So that's the derivative of theta, and you can see it depends on this difference f minus y, and also this gradient. Okay, that's the derivative of theta. So the reason this equation is no good is because it says the derivative of theta is stuff involving f. So that you can't solve that because the derivative of theta is something outside of our control. We don't know what it's doing. So this is the key insight: is don't look at the derivative of theta. What we really want to do is look at the derivative of f. So this is, I think, the smart thing, that we're going to use this equation, but it's not the final endpoint. So that's the gradient flow rule for the derivative of theta. Now we look at the derivative of f. What's the derivative of f? Okay, and of course this depends on theta, so there's going to be another chain rule. So this is chain rule one more time to get this. So the derivative, the time derivative of theta of f of x theta t is the time derivative of theta times the gradient of f. So this is another chain rule, and this one looks like this: d dt of theta t. So this one is an n par by 1 vector, and this one is a 1 by n par row vector. So this is more chain rule, more chain rule. Okay, and we have a formula now. We have a formula for this guy. We can plug that in. So the formula for the derivative of theta is what we just did. So we can plug that in. It's just the gradient of f x theta t times f of x theta t minus y with a minus alpha in front. Okay, let's make sure all the dimensions here line up. This is an nx by 1. This is a n par by nx. And this is a 1 by n par. And that's the final situation. So the derivative of f, it depends on the gradient of f times how f is doing on the training set, f of this script x and script y. And you might not recognize it, but so this thing, so the gradient of f transpose times gradient of f, this is actually just the kernel k. This is actually the kernel k of x, script x. And what I've written so far is true for any gradient descent model. So the fact that the time derivative of f is always this kind of formula, where you have the gradient of f transpose times the gradient of f, that always works. The thing that is a miracle in our model is that in general, this will depend on theta of t. And if you're doing the time derivative of this thing, and it depends on theta of t, and you don't know what theta t is, there's no way to solve it. But in our model, because it is a linear model, actually this thing is always this kernel k, and it doesn't depend on theta t. So maybe there's one more step, which is if you do the gradient of f of x comma theta t transpose times the gradient of f x prime theta t, this is always k of x prime, no matter what theta t is. And that's the miracle that makes this thing work, is that these gradients don't depend on the parameters, they only depend on the x values. And the reason that works is because it's a linear model. So since f of x theta is equal to theta transpose phi of x, that's a linear model, so when you do the gradient, it's very easy to do the gradient. It doesn't even depend on theta, it just is phi of x. Oh, I believe we had a 1 over square root of n par to make things work. Let's put that back in. So that is the gradient. So when you calculate this thing, you get exactly 1 over square root of n par phi of x transpose times 1 over square root of n par phi of x prime, which is exactly what we defined to be the gradient. So this is 1 over n par phi of x times phi of x prime transpose. And that's exactly what we defined to be the kernel k. So you can see how the kernel k came into existence. The reason it works so well in this in this simple model is because the model is linear, so that these gradients, they don't actually depend on what's happening at theta t, and that's why we got this really simple equation. So this is a good trick. You can always do this trick up to here, and then you can ask yourself, in what way does it depend on theta of t? And linear models are so nice because it doesn't depend on it at all. So the kernel does not depend on the parameters. So that's part one. Part one is showing that we satisfy this equation. And again, you can read the notes as well. That's part one. Part two is to solve it, and I'll do that in a separate video. So part two is we're going to solve. We're going to go from this thing to this thing. This is like solving a differential equation. So if you took a class on differential equations, you might need to refresh your notes from that.